Hello, everyone. Thank you very much for joining us today for our live session. I'm going to hand over the session to Professor Impey to get us started, and then we'll do questions.
Okay, welcome everyone to another live session for the online classes, and we'll just get right started. Floor is open. Matthew lost audio.
Oh, I'm sorry about that. So the first question from Junaid Atta, who is on with us live today, asks, if the universe is expanding, then how is it possible that Andromeda will collide with the Milky Way?
Yeah, good question. Seems to run against the notion of Hubble expansion. So the expansion of the universe is something that applies on large scales. It's basically space-time itself expanding. That is the vacuum of space, the fabric of space, so to speak, is expanding, and it carries objects within it at further and further distances. But those objects do exert mutual gravity. So the galaxies will pull on each other by their own gravity, and that essentially runs counter to the general expansion of the universe. So on very large scales and with distances of tens of millions of light years, typical galaxy-galaxy distance is about 1 million light years. But on scales of tens or hundreds of millions of light years, everything is moving away from everything else. However, on smaller than about 10 million light year scales, and in particular on a few million light year scales, galaxies are massive enough that their mutual gravity can cause them to exempt themselves, if you like, from the cosmic expansion and move towards each other. And that's the case with the Milky Way and Andromeda. Andromeda is about 2.25 million light years from the Milky Way, and that's close enough that their mutual gravity means they're no longer moving apart as the universe expands and are moving towards each other at about 100 kilometers per second. And that speed and the pretty much direct approach suggests a collision or an encounter, a very close encounter, in about 3 or 3.5 billion years. And that is true elsewhere in the universe. There are clearly situations where the density of galaxies in a region of space is high enough that they're bound by gravity to each other, and that's what a cluster of galaxies is. And so we know of the Virgo cluster, the Coma cluster, and hundreds of clusters in the universe that are held together by their gravity of one galaxy to another, and so are not expanding with the cosmic expansion.
Thank you very much. The next question is again from a live viewer, Himanshu Singh, who's on with us live, who asks, is there any reason why time has only one direction?
Not clear. There should be a reason. I mean, it's a phenomenon that's quite interesting because in physics, things tend to be symmetric or reversible. Space has no preferred direction, for example. Three-dimensional space has, X, Y, and Z dimensions, and there's no preference between the dimensions. So physics is also full of interactions at the level of subatomic particles that move forward and backward in time. So if you have a particular particle reaction that occurs in one direction, you can make the conditions such that that particle interaction will occur in the opposite sense. So at the level of individual subatomic particles, time's arrow does actually seem to be reversible. So the question is, where does the irreversible arrow of time kick in? And apparently it kicks in for large numbers of atoms or for macroscopic objects. So in the universe full of sizable objects like planets and people and stars and galaxies, there is an arrow to time, and it's presumably related to disorder or entropy or the number of equivalent microscopic states of a system. From a starting point of relatively high order or an unlikely configuration, the system will interact and move towards a more disordered situation, which is more likely occurrence, because there are many more ways for a system of particles or objects to be disordered than to be highly ordered. And so that's the sense of the arrow of time. That doesn't completely answer the question, but it suggests that the answer to the question comes in the consideration of large numbers of objects, statistical mechanics, as we would call it in physics.
All right, the next question is from WS, who's on with us live. And the question is, why are we able to see the cosmic microwave background, but not see the youngest galaxies that formed after and thus are closer to us in spacetime? Shouldn't the cosmic microwave background be outside our cosmic horizon?
That's an interesting question. So we see the cosmic microwave background, and that is essentially the radiation that was released to travel freely in the universe when atoms got cool enough, or when particles in the early universe got cool enough to form stable atoms. And but prior to that point, electrons and protons careening around essentially meant that light would always scatter off the electrons. That's called Compton scattering in physics. And it means the universe was opaque. As the universe cooled, those electrons became attached to the atoms. There was no longer an impediment for radiation traveling, and that's what we see as the microwave background. And that dates to a very particular time. It's about 400,000 years after the Big Bang, or a redshift of about 1,000, very close to the Big Bang. And so the question of why can't we see things after that is interesting. And it's really because after just chronologically moving forward from the time of the microwave background, the temperature of the universe was about 3,000 Kelvin. As the universe got cooler and bigger and continued to expand, and stable atoms had formed, it just essentially became a cooling object. And so if it emitted radiation, those microwaves would have redshifted through into infrared regime. And essentially, the universe would have been invisible if you could see the whole thing. And then nothing really happens until gravity has had time to act, and the first stable structures form. And the first lights go on in the universe with the formation of the first stars and galaxies. So this is called the Dark Ages. So the Dark Ages stretches essentially from the time the microwave radiation was released, around 500,000 years after the Big Bang, until a time that we don't quite know exactly, but probably 100 to 150 million years after the Big Bang, when gravity forms the first stars and galaxies to collapse. In the intervening period, the universe is dark. It's still evolving, it's still growing, it's getting more diffuse, it's getting cooler, and gravity is finally having a chance to act for the first time.
Sorry, thank you very much, Chris. The next question is from Elaine Nora, who's on with us live, who asks, I read an article that scientists have managed to see an electron. Is this true? And how is it possible to see an electron?
Right, that's a good question. Electrons are very tiny particles. In fact, measuring the size of an electron is quite a difficult physics experiment. Well, but also remember, in quantum theory, every particle has an equivalent wavelength. It was Willem de Broglie, a famous physicist from the early part of the 20th century, who was working at the same time as Heisenberg and Planck. De Broglie recognized that particles have equivalent wave-like properties, and so a particle has an equivalent wavelength. So the wavelength sort of defines the size of a particle, and the equivalent size of an electron is exceptionally small, obviously thousands of times smaller than an atom itself. So the only waves of radiation with which you could see an electron are waves smaller than that could scatter off an electron and so say where it is. And those waves have to be extremely high energy. They basically have to be gamma rays. And so with very high energy, with very short wavelengths radiation, you can in principle pinpoint the position of an electron. But there's a problem. Those very short waves correspond to very high energies. So the same experiment that scatters a photon off an electron, and the photon wavelength is small enough to say where the electron is, has such high energy that it gives the electron a large amount of energy and sends it somewhere else. This is the uncertainty principle in action. So these experiments to measure the size of an electron are compromises because they don't allow all the properties to be measured at once.
All right, the next question is from Jaspreet Singh, who's on with us live, who asks, is the Large Hadron Collider an example of pair annihilation and pair production? How exactly does that work?
The Large Hadron Collider is able to make many different particle interactions occur, including pair production and pair annihilation. Basically, the Large Hadron Collider is sending two opposing beams, protons and antiprotons, towards each other, and the center of rest mass energy of these collisions is many giga electron volts, hundreds of giga electron volts. And in that situation, the pure energy of the collision can be used to create particle-antiparticle pairs, which will then come in and out of existence as the antiparticles annihilate with matter that happens to be in the vicinity. So yes, the Large Hadron Collider works essentially by turning collision energy into the potential to create both particles and antiparticles. And since baryon number is conserved, they will be created in equal numbers, and the antiparticles will subsequently annihilate and disappear into radiation.
Thank you. The next question is from P.T. Cruiser, who's on with us live, who asks, as Mars is not capable of sustaining an atmosphere, what conditions were different before, since Mars once must have had a more Earth-like atmosphere with clouds and rain and all sorts of different atmospheric phenomena?
Right. We see clear signs in the geological record of Mars, this both from observations. This was known to orbiters 50 years ago and the first landers, and it's been accentuated by the rovers that have been sent there in the last few decades. We have very good evidence that Mars at one point had water running across its surface and perhaps shallow seas that were long-term stable. There's a debate in the planetary science community about how long-lived those bodies of water were, but they definitely existed for, at least hundreds or thousands of years at a time. For Mars to have held water on its surface, it had to have a much thicker atmosphere, and it had to have been warmer, because Mars is currently too cold for liquid water to exist on its surface. And so we don't know exactly what the conditions of Mars were, say 3 billion years ago, when liquid water seemed to have been on the surface, and we don't know totally what happened to make the atmosphere go away. But the basics are pretty clear, because Mars is a much less massive object than the Earth, and so the gravity with which it holds gases in its atmosphere is weaker, and those molecules eventually diffuse into space. And that's because the molecules in a gas at a particular temperature have a range of kinetic velocities, and the higher velocity tail of that distribution can exceed the escape velocity of the planet, and so they gradually escape and the atmosphere will leak into space. So that's what we think happened. Gradually, Mars lost its thicker atmosphere, which may never have been, of course, as thick as the Earth's, and was not made of the same things, of course, since Mars has no oxygen to speak of, because it had no surface life as far as we know. It gradually leaked its atmosphere into space, and at that point, the planet could freeze. The bodies of water would both evaporate and freeze and just turn into subsurface ice and dry ice, which is what we see now. And it becomes a cold desert, and that's what we see now. So the pathway by which Mars went from warmer and wetter to what it is now is well understood. But it's interesting that the climate models to fully account for large bodies of water on Mars 3 billion years ago don't quite work.
All right. The next question is from an email from Anthony Lynn, and I'll try and phrase it the way I think they're understanding, but it's possible that that they're asking about pulsars. But the question is, can you explain the process by which cosmic rays from neutron stars interact with the magnetic field of the neutron star to form radio waves?
Okay, I think I understand the question, but basically, what is it about a neutron star that leads to hotspots, which is what a pulsar is? So I'll give that general scenario. A neutron star is pure neutron material, of course, caused by the collapse of the core of a massive star. And that pure neutron material, electrically neutral, has the density of an atomic nucleus. Now, a pulsar is a physical object, and it's compact and spinning very fast because angular momentum was conserved when it collapsed. So the core, the neutron pure material, is spinning very fast. We've seen examples spinning hundreds of times a second. And even a typical pulsar with a period of maybe a tenth of a second is spinning 10 times a second. So these are very rapidly spinning objects, and they have imperfections. So they're essentially seismic activity associated with any neutron star. Some of this is just mild reforming or fissures in the neutron crust that gradually settle and change the spin rate momentarily. But pulsars can also have hot spots, and that typically happens at the poles. The magnetic field that threads a pulsar is able to accelerate photons. That's a process called cyclotron radiation, and has very high polarization, that radiation. And that is the essence of what we see with a pulsar. So particle acceleration at the strong magnetic field poles of a pulsar coming outward in a beam will intercept a radio telescope and give pulses, radio pulses, and that's what people see as a pulsar. So for that to be the case, the star has to have enough imperfections and enough particles nearby to be accelerated to make radio emission. And of course, the beam, which is quite narrowly focused, has to happen to be pointed at your radio telescope. So for every pulsar that radio telescopes see, we can infer a significantly larger number, dozens of times larger number, for which the radio beams, the beams of accelerated photons, are not visible to the radio telescope. So we have to infer the total number of pulsars, or neutron stars, from the number of pulsars that we measure. Currently, there are about 4,000 pulsars in radio catalogs.
All right, thank you very much, Chris. The next question is from Alexis Frey, who's on with us live, who asks, do you think we should devote our time and effort on terraforming Mars or on building O'Neill cylinders and other space-based habitats?
It's an interesting question. I hope we don't have to leave the Earth. I don't hope we take care of the planet well enough that we don't have to leave the Earth. But if we did have to leave the Earth, how would we do it? So it's a good question. If more than the modest number of astronauts, only 600 people have ever been in Earth orbit, it's a really small number. Even if it gets cheaper and easier, it's not likely that a large fraction of the people will leave the planet. Terraforming Mars is an enormous undertaking and an expensive undertaking, and it could not be done quickly. In fact, it couldn't be done, I think, in less than a millennium. NASA has had various design studies over the decades, and the methods by which you would gradually raise the temperature of Mars, liberate the liquid water, start to form an atmosphere, start to seed the atmosphere with oxygen from primitive microbes, and build a breathable atmosphere at near pressures of the Earth. That's a three-stage process that takes centuries, essentially, with the best possible technology. And it all happens a large distance from the Earth, so you have to get material out there. So it's extremely hard to do and extremely expensive. O'Neill cylinders, which were, Gerard O'Neill was a space visionary who, starting in the 1960s, wrote these beautiful articles and illustrated books imagining what it might be like to live in space wheels orbiting around the Earth. Those are enormous constructions, of course, but they're actually much easier to imagine we could build than to terraform Mars. The missing piece to do this at all is a space elevator. Once you have a space elevator, which is a cable running up into space, whose tensile strength is enough that you can balance the weight of the cable against the centrifugal force of the Earth, and it just hangs there out into space. That lets you bring things from Earth's surface to zero gravity essentially for free, because you can use solar-powered lifters rather than rocket fuel. If you had a space elevator, then your ability to construct large things in Earth orbit becomes much more plausible, and so it could actually be done. So I think O'Neill-type habitats are not implausible for substantial numbers of people, not really the population of the Earth, but I'm talking about thousands or tens of thousands of people. And that could be done, maybe in a few decades, certainly in 50 or 60 years, so much, much faster than we could ever make Mars habitable. And the cost of getting people to Mars, let alone the cost of transforming Mars, is phenomenal.
Thank you. The next question is from Mark Chalecki, and The question is from an email. What do you think will be the next great astronomical discovery or discoveries?
Well, the biggest, of course, would be life beyond Earth. And I don't know if it'll be the next great discovery, but it could be. Astronomers are getting close to the methods they need to dissect and sniff the atmospheres of Earth-like exoplanets. And we have plenty of candidate exoplanets to do this experiment with. The limitation is having a big enough telescope to disperse the feeble reflected light from an exoplanet. If it's an Earth-like planet around a sun-like star, it's a billionth of the star's radiation, and then it's turned into a spectrum. That's a very difficult experiment. Big telescopes can do that soon, and adaptive optics is also needed to sharpen the light from the star to be able to separate the planet that's nearby in the plane of the sky. That's my guess for the most likely big discovery in astronomy, where atmospheric spectra are taken that indicate biomarkers that see oxygen, water vapor, methane, ozone, all the tracers of non-equilibrium chemistry that on the Earth indicate life.
Thank you very much. The next question is from one of our live viewers from Greece. And the question is, under what circumstances would we define an exoplanet as habitable?
It's a tricky definition. It's been mostly done in a very schematic way. Typical habitability calculation just means how far from the parent star would the surface of the planet have a temperature between the freezing point and the boiling point of water, 0 and 100 degrees C. That's a limiting calculation, but that doesn't take into account the effects of the atmosphere of the exoplanet. The atmosphere of an exoplanet will act like a blanket, a warming blanket, and so that immediately changes that distance calculation. So you have to make assumptions about the atmosphere of the exoplanet, and then you can talk about habitability. The next thing to take into consideration, if you had the information, was the eccentricity of the orbit and the orbital tilt of the planet around the star. If the eccentricity of the orbit was too large, the seasonal variation in temperatures would be so large as probably to make life unsustainable on the planet. If the orbital tilt was too large, the same thing applies. Uranus in our solar system has 42 years of summer followed by 42 years of winter because it's tilted on its side. Earth, with a 23.5 degree tilt, has seasons, but they're not so extreme as to make life impossible. So really you need those two extra pieces of information to make a more reasonable habitability argument, along with we need to know the composition of the atmosphere of the exoplanet. And we have that level of information for very, very few, just a handful of exoplanets.
The next question is actually from a couple of people. There's an email about this, and David, who's on with us live, would like to know this as well. And the question is, why isn't Europa our main destination for looking for life in our solar system? And sort of relatedly, which is more likely to support life, Europa or Enceladus, and why?
Europa is a major destination. NASA planned the Europa Clipper mission some years ago, almost a decade ago, and it has the green light. And so it is going to be a Europa mission, which will get there in 5 or 6 years, I think. It's going to be mostly an orbiter. It's planning to splash objects into the icy surface and then sniff the material that gets knocked off the surface. So that's a sophisticated, expensive international mission to Europa that's going to go some way along the road to understanding whether Europa might have life on it. Enceladus is an interesting target, but it probably doesn't knock either Europa or Titan off the hot list of places planetary scientists want to go. And that's just because Enceladus is so small. It's almost asteroid size, so it's a very small moon of Saturn. And it seems by tidal flexing to have enough heat in the interior to have liquid water in its interior that bubbles up and forms these geysers or jets that have been observed by Cassini and now also by ground-based telescopes. It may be a little unlikely to think of Enceladus as having life, though. And it's just a very small world. So I think the best bet, if people are placing bets, is to take one of the more substantial moons as a place to do life sensing experiments.
Thank you very much. All right. The next question is from one of our live viewers. And the question comes from Bert Kummel, who would like to know, are American telescopes now part of the new Space Force?
No, not directly. The Space Force has only just been constituted. The Trump administration has declared that there will be a sixth service agency in the military, and it's the Space Force. The amount appropriated by Congress for this is really tiny. So the Space Force is not going to happen very fast, and it's not still entirely clear what the Space Force will do. But it will be a mixed civilian and military agency. It's under the auspices of the military. It's not going to take the existing telescopes under its wing, because the telescopes like the Kidd Peak telescopes are telescopes run by universities, like here the giant Magellan telescope that's going down to Chile, and the ones we have on our mountaintops here. They're not government owned or government run. So many of the largest telescopes in the world were built with federal money, but also in collaboration with corporations and universities and research institutes. And so they're not really going to be usurped from their original purpose.
Thank you. The next question is, again, from a live viewer who would like to know, sorry, I got a little lost in here. The question is from Josh Kilburn, who would like to know, where did all the magnetic monopoles go?
Well, assuming there were magnetic monopoles, they must have annihilated or possibly just evaporated. I don't know what the mechanism might be. The reason the question is interesting is it is understood in early Big Bang physics that you could create monopoles. The curvature of space-time in the very early universe and the density of matter and radiation is such that you have topological defects. A monopole is like a topological defect in space. And in the theories from these very early ages, these monopoles could survive. So you could have topological defects that survive until the universe is older and colder. Astronomers have had indirect ways of measuring the existence of these things, and none has ever been detected, and the limits are quite severe. So it does look like they don't exist in the universe in any large number. And that could be because the unified theories we have that predict monopoles are actually wrong. Grand unified theories have not done very well with the results from CERN. They haven't been validated by the best results from the Large Hadron Collider. So I think the jury is out on whether we even understand the theory that predicts monopoles, let alone whether they actually exist in significant numbers, which they don't.
The next question is from a live viewer, Spacetime, who would like to know what the latest is with Betelgeuse and when do you think it will go off?
It's under very close scrutiny, of course, having shown these variations, and especially the dimming part, which some people think is a precursor to it running out of nuclear fuel and going into a new volatile, fast late-stage evolution phase. As I recall, or as far as I've seen, nothing dramatic has happened with Betelgeuse recently. It's still showing variability. It's overall showing fading in its brightness. It's consistent with the exhaustion of nuclear fuel that might be imminent. But imminent in astronomy is a tricky term. It could mean in weeks, months, or even years, or decades. So we don't know the evolutionary state of Betelgeuse well enough to predict when it's going to go off, and that's the problem. So we're just left observing it and wondering if we can use those observations of a late-stage star evolution to refine our theories of stellar evolution. That's really how it's being used right now, rather than predicting when it's going to go off.
Thank you very much. The next question is from the Daily Artonaut, who's on with us live, who would like to know, can the mass energy equivalence, represented by E equals mc squared, be used for dark matter and dark energy?
It's a good question. In principle, it could be, because it's stating a fairly profound aspect of the natural world as articulated by Einstein and by the theories of relativity, general and special. Dark matter, yes, dark matter, since we think it's a fundamental weakly interacting particle, it would have an equivalent energy, such that, for instance, if you had energy in particle beams of sufficient threshold in energy, you could create the dark matter particle with the appropriate mass. And that hasn't actually ever happened. We don't really know what the mass of the hypothetical dark matter particle is. As for dark energy having an equivalent mass, that's less clear, because dark energy is not a form of, obvious energy you can ascribe to an object like kinetic energy or potential energy. Dark energy is a feature of the vacuum, and so it's not clear that dark energy as an aspect of the vacuum has an equivalent mass. It probably doesn't.
All right. The next question is from one of our live viewers who would like to know, this is from D. Zach, who would like to know if you have a favorite planet or object in our solar system and why that is.
Well, in our solar system, I kind of like Titan because Titan is so exotic. It's a large moon of Saturn that's got an atmosphere as thick as the air you're breathing, made of mostly the same thing, nitrogen. It's a big moon. It has bodies of liquid on its surface made of methane and ethane rather than water, although there may be a little water mixed in there. And it's a very dynamic world. It has cryovolcanism, so there's some geological activity. Tidal stretching by the parent planet keeps it a little warm in the interior and causes volcanism, but it's a kind of icy volcanism unfamiliar to the Earth. All of these things plus the existence of the hydrocarbons themselves, one of the ingredients of life, make it a fascinating place. There's a Dragonfly mission that NASA's envisaged, which is a set of drones, or at least one drone, that will hop around Titan, making measurements of its liquid bodies and the chemistry therein. This is a very exciting mission using sort of cutting-edge drone technology. It's a decade or more. It's even a few years from being approved, and it's a decade or more from being launched and heading to Titan. But that would be my bet for favorite object.
Okay, the next question is from a live viewer. Ryan would like to know, can a large enough star turn into a black hole without going supernova?
It's an interesting question. As far as I know, no. The supernova phase, which embeds within it the idea of core collapse, that when the star is no longer supported by energy released from nuclear reactions, there's a gravitational collapse, a dramatic and a catastrophic gravitational collapse. And it's really that collapse, uncontested by any new force of nature, and that compression that leads directly to the density of a black hole. So I think those two things go very closely together. You can't have one without the other.
All right, the next question is from a live viewer, Trey. We'd like to know, how has our improved understanding of quantum mechanics changed or affected our understanding of the universe or multiverse as we know it?
We do understand quantum mechanics better than we did when it was first proposed, but not enormously better. I mean, some of the philosophical issues that were brought up early when the quantum theory was proposed have not been fully resolved. The question, for example, of the uncertainty principle, the question of entanglement, the sort of philosophical issue of what measurement means in a quantum system, these issues haven't been completely resolved. They stay in a philosophical realm. And the entanglement in particular has raised the specter of non-local physics, which means somehow instantaneous effects across significant distances of space between particles that are coupled in an entangled state. That's not really well understood. So our improved idea of quantum mechanics is only up to a limit. There's still some profound mysteries in the quantum theory. Operationally, it works very well. We can calculate quite easily in the quantum theory, and it predicts the way the particles will behave. But as far as insights into our universe, that's much thinner. We know that quantum theory and quantum interactions pertained very soon after the Big Bang, but that's a part of the cosmic history that we're really dimly aware of and don't know how to measure. So again, we're talking about a lot of speculation.
All right. The next question is from Jaspreet Singh, who would like to know, what do you think about the sun's solar cycles? What causes the solar cycles, and why does it go through these sort of hibernation phases where there's not much going on with it?
So solar cycle is triggered by the magnetic field of the sun. So it's a 22-year cycle, which represents the sun's magnetic field forming from a chaotic state where the magnetic field's really weak, getting twisted up and entangled because the sun rotates differentially, rotates faster at its equator than the poles. The magnetic field lines reconnecting, the magnetic field dissipating, and then reforming with the opposite polarity. So each of those is a half cycle of 11 years, and when it goes through that same sequence with the opposite polarity, that's the second 11 years, leading to a full 22-year solar cycle. The mechanisms by which the sun's field builds are well known as the dynamo mechanism. That's physics that goes back 50 years. It's complicated to apply that physics theory in the messy, complicated object like the sun, but it works fairly well. So we think we know how magnetic field can build from weak seeds, can grow, can become wrapped up and entangled, and then eventually do massive reconnection, dissipate, and then reform. What sets the timescale is the sort of density of the sun and its rotation rate. Different stars will have different sunspot cycles and solar cycles. And we've been able to measure some of those in the last few years.
The next question is from Franco Harris, who's on with us live, who has kind of a space travel or human spaceflight question that also goes into some basic physics. So on spacewalks, why is it that the space station doesn't yank the astronauts from their ropes because it's going so quick?
So everything is co-orbiting. When astronauts exit the space station through an airlock, they're sharing the motion of the space station in its rapid Earth orbit. And since there's no friction in space, because there's no resistance, there's no medium, it's a vacuum, objects continue their motion. So when an astronaut leaves either the shuttle or the space station, they will essentially be floating alongside it at the same speed the huge object of the space station is orbiting. So that's the easiest way to understand these phenomena, that the objects are all moving together in an orbit, because the orbital period doesn't depend on the mass of something, it just depends on its distance and the mass of the primary object, the Earth.
All right, the next question is from Josh Kilburn, who's on with us live, who would like to know, how is it that we detect neutron stars? Is it possible there are neutron stars close to Earth that we just haven't found yet?
Yes, we only detect neutron stars when they have the imperfections and hotspots that lead to radio emission by the cyclotron mechanism, and that turns them into pulsars. So pulsars are the small subset of neutron stars. We think quite a small subset that have radio emission because of these orbiting hotspots that rotate and swing a beam of radio emission through the beam of a radio telescope. So there are a large number of unseen neutron stars, and the question could be, where is the nearest one if we can't see them, especially if it's an isolated object? We can just say statistically that since neutron stars are rare, because most stars do not die and leave behind that kind of a remnant, they die and leave behind a white dwarf remnant, as our sun will do. You're talking about a much rarer set of stars of 4, 5, 6 solar masses. And that scarcity of those high mass stars suggests that the nearest neutron star, even if we can't see it, statistically it's going to be tens of light years away. So we think there are no neutron stars very close by.
Okay, the next question is from Frank Allen, who's on with us live, Says, I've always been fascinated with black holes. What are the latest theories about what to expect if an object were to travel inside one? Could it survive the intense gravity in any way?
It depends on what the object is and what type of black hole. For a stellar black hole, the kind that dies when a massive star dies, leaves behind, say, 3 times the mass of the sun black hole. The tidal forces of gravity when you're close to the event horizon are phenomenal. So any physical object, like a person or an asteroid or a meteor, will be ripped apart. Stars will also be ripped apart. Typically, when a small star falls into a black hole, its atmosphere is torn from it as it falls in, and then the star itself is completely disrupted as it falls in. So there's no structural integrity of any physical object, gaseous, solid, or liquid, falling into a low-mass black hole. When the black hole gets bigger, though, and there are bigger ones elsewhere in the galaxy, the tidal force becomes weaker. The total gravity is stronger because the mass is high, but the stretching force, due to tidal forces, actually goes down for bigger black holes with bigger event horizons. And at some point, objects would survive intact, and that transition is for usually black holes of a couple hundred up to about 1,000 times the mass of the sun. There are objects where something could survive the passage into the event horizon.
In sort of a related question, Tom, who's on with us live, would like to know what your views are on what Professor Leonard Susskind calls the Zeroth Law of Conservation of Information. What does that mean, say, in the context of something that falls into a black hole?
If Susskind is right, then information is not lost or destroyed in a black hole. One version of this idea is the holographic theory of black holes, where the information, as it falls into the event horizon and is seen from the outside, sort of takes an asymptotically large amount of time to hit the event horizon. That information is not lost. It's essentially coded or mapped straight onto the event horizon, where in principle it can be decoded. The preservation of information is not guaranteed. Susskind is basing his premise on the fact that in particle interactions, as almost an ironclad rule, information is conserved when a particle interacts forward or backward. But in a black hole, that reversibility is lost, because if the particles interact and one falls into the black hole, or they both move into the black hole, that information is no longer available. To get around this, people have invoked a firewall, where somehow entangled states, when they are broken, such that one particle falls in and the other stays outside in the visible universe, create a firewall, a sort of intense burst of radiation that destroys all information. And that's why you can't get the information out. So you have to think of a reason why the information can't get out, given the reversibility of quantum theory in the everyday world.
Okay, the next question is from Bob Callahan, who's on with us live, who asks, the Giant Magellan Telescope is expected to see first light in 2022. What might it see when it turns on? Like, what are some of the first things that it will be looking at, and was it designed to look at?
So the Giant Magellan Telescope, it's 6 of our 8.2 meter mirrors made in the Mirror Lab on the University of Arizona campus, around a central petal of the same size, has an equivalent diameter of about 22.5 meters, would be the largest telescope in the world. Construction has started on a mountaintop in Las Campanas in Chile, and everyone's very excited because this would be the first of the giant telescopes to be completed, the other two being the Caltech California 30-meter telescope and the European's extremely large telescope, also bound for Chile. What these telescopes will do initially is this kind of science that only they can do, and sniffing the atmospheres of exoplanets, looking for biomarkers. That's clearly one of the key projects for a Giant Magellan Telescope. We need adaptive optics because you need super sharp imaging to be able to isolate the feeble reflected light of the exoplanet. But that's a key measurement that's going to be done in the first couple of years. Also looking at high redshift galaxies and maybe trying to untangle the growth rate of the most massive black holes in the universe, which is a bit of a conundrum because we see quasars or active galaxies with multi-billion solar mass black holes that are active, and they've somehow formed, and the black hole have grown to that huge mass in well under 1 billion years, maybe half a billion years. That's a puzzle. So the Giant Magellan Telescope will be pushing forward in that. It will observe objects in the solar system with unprecedented resolution. It'll look at the faintest stars in the galaxy and the universe to look at the boundary between white dwarfs, red dwarfs, and brown dwarfs, the stars that barely shine at all. And it will also, of course, study very faint supernovae at large distances, try to get a handle on the cosmological expansion rate. So many projects for the GMT. It's a very exciting big telescope that's now on the horizon, just a few years away from first light.
All right, the next question is from an email from Anthony Moore, who would like to know, how large can a star grow, or is there an upper limit to how big a star can grow?
There seems to be an upper limit. So astronomers, mass is not the easiest thing to measure for a star. It's easier to measure their brightness, of course, make a spectrum and measure a bit of their chemistry and to talk about how many heavy elements they have. And if you can get the distance to the star, then you know its luminosity, so you know where it is in a Hertzsprung-Russell diagram. Mass is hard to measure, but we can sort of infer mass from luminosity. And the most massive stars, it's a bit of an argument and debate in the literature because the masses are uncertain, are about 150 times the mass of the sun. There are a couple of claims out there of stars about 200 or 220 times the mass of the sun, but to be honest, there have been skeptics about those calculations or inferences. So let's say that probably 200 is the absolute limit for a star's mass. That object is so massive it collapses catastrophically. It destroys itself almost before it has a chance to have a main sequence life. And of course, it will leave behind a black hole based on current theory.
The next question is from Debaparna Goswami, who's on with us live, who asks, how do astronomers differentiate between the Doppler shift, cosmological redshift, and gravitational redshift?
So these three redshifts are important to keep distinct. Cosmological redshift is redshift induced by the expansion of space-time. And the easiest way to keep that straight is by having a distance measurement to an object, because in the Hubble regime, in the Hubble expansion, distance and redshift are very specifically related in terms of an expanding universe model. So when you know distance, it's fairly trivial to understand that you're looking at cosmological redshift. Gravitational redshift tends to be very small, so unless the object is exceptionally dense and compact, the gravitational redshift of whatever object it might be is going to be dwarfed by its cosmological redshift, for example, if it's in a distant galaxy or moving away from us fast. The third form of redshift, the Doppler shift, really only applies for local objects. And so in the solar system or within the galaxy, we can talk about Doppler shifts. These are all situations where the cosmic expansion doesn't come into play because the galaxy is not expanding, nor is the solar system. These systems are held together by their mutual gravity. So on small scales, it's fairly easy to keep Doppler distinct from cosmological, and it's fairly easy to keep both of those distinct from gravitational, because unless you're in a super dense gravity regime, gravitational redshift is tiny.
The next question is from William Spizzeri, who's on with us live, who would like to know, are there any new theories or new ideas or new data about the great early asteroid bombardment on Earth?
It's become a little controversial. So the great asteroid bombardment, or alternatively the great heavy bombardment, is a period of time from about 3.7 to 3.9 billion years ago, when in the cratering history of the Moon and with less precision Mars, there appears to have been a spike in the impacts. So generally, the large debris left over from the formation of the solar system slowly declines as those chunks of rock, those planetesimals, are built into planets, and then eventually the smaller ones swept out of the system by radiation pressure from the young sun. And so all of the ideas of formation suggest that impact rates should just steadily decline from the origin. So seeing this sort of surge in impacts well into the era of the solar system being fully intact, so this is again 700 million years after the formation, was a surprise. And it's now been imputed that this time was a time when there was a major rearrangement of the planets, sort of essentially a migration process akin to what happens with exoplanets, and that as the planets started moving and were in harmonic oscillations that made instabilities in their orbits, then you can have dramatic influx of material from outside. Essentially, when the planets rearrange, they could kick asteroids from the asteroid belt into Earth-crossing orbits. They could perturb the comet cloud and send flux of comets into the inner solar system. So there are mechanisms to get a heavy bombardment. But the evidence for it on the Earth, of course, is not there because the crater history of the Earth is highly incomplete because it's a water-covered planet, and it was then too. So I would say heavy bombardment is still a hypothesis that it happened on the Earth. It's certainly intriguing that the earliest evidence for life on Earth appears to predate the era of heavy bombardment. So life, having got started, must have had to survive this dramatic period of time. In some of the models of the heavy bombardment, there are Earth sterilizing events because some of the impacts are so large. So possibly life got started, got wiped out in the bombardment, and then had to get started again. That's a very fascinating conjecture.
All right, this next question is from Spacetime with Robert, who would like to know, since the expansion of the universe has slowed down enough for light to reach other galaxies, how long has the Andromeda galaxy been observable from within our Milky Way galaxy?
So Andromeda has always been observable since both galaxies formed because Andromeda has always been fairly close to us physically in space. In the early part of the formation, when the Milky Way and Andromeda were being formed by collisions of smaller galaxies, remember in hierarchical structure formation with cold dark matter mediating it, we have a bottom-up structure formation where small galaxies form first and they combine to form more massive galaxies. So depending on the models, it takes 1 billion or maybe more years for a fully fledged galaxy like Andromeda or the Milky Way to form. And early on, of course, the universe was smaller and denser and hotter, and so the young Milky Way and young Andromeda were closer together than they are now. They started to move apart, and then at some point, their mutual gravity, as they each grew and got bigger, started to pull them towards each other. So they've gone through an interesting little stately dance already, even before they enter their collision phase in a few billion years.
The next question is from Edri Safi, who's on with us live, who asks, why do objects make space-time curve?
It's a core premise of general relativity that mass curves space-time. So Einstein came up with the geometric theory of gravity, whereas Newton just hypothesized this force that acted over the vacuum of space, over an infinite range, in fact, simultaneously holding objects remote in space to each other in orbit and so on. Einstein came up with a different idea, which is based on geometry, that objects would follow what are called geodesics, which are minimum energy paths in space-time. And the way that happens when there's mass is that those geodesics or trajectories can be curved. And so when objects are in orbit around each other or deviated as they move close to each other or have glancing encounters, that's literally because of the curvature of space-time. And so it's just a different way of thinking about gravity, and it's a very interesting way of thinking about space-time, but it seems to be correct. It's been validated by all measurements so far.
All right, the next question is from a live viewer, and the question is, what is the largest possible diameter that a black hole can have? How large? Okay, that's I guess that's a separate question. So what is the largest possible diameter that a black hole can have?
Well, it depends on the black hole. So black holes are interesting because their mass scales with their radius, their Schwarzschild radius. That's the distance to the event horizon, essentially. So we can scale from the low mass black holes, the lowest mass black hole when a 10 solar mass star dies and leaves behind a 3 or 4 solar mass black hole, that event horizon is a few kilometers. So for one solar mass, the event horizon or Schwarzschild radius is 3 kilometers. So when we can just scale up from that. So if you have a billion solar mass black hole, its event horizon or Schwarzschild radius size is 30 billion kilometers. And we know that's about a solar system size. The biggest black holes are about 10 or 20 billion solar masses. So that's 10 or 20 times larger still. So now you're talking about 100 or a few hundred billion kilometers. And so the very biggest black holes that we've ever seen are 10, 20, 30 times the size of the solar system. Is that the absolute limit? We don't know, but there is an absolute limit to the size and mass of galaxies, so there probably is a limit to the mass of their central black holes, and I don't expect black holes get much bigger than that.
So then the related question is, how large does a black hole have to be so that it has a surface gravity of 1g, so like Earth gravity?
Well, to have a surface gravity of 1g, the gravitational force at the surface would have to be equivalent to an Earth mass operating at that distance. And so no black hole is in that regime. Their gravity is all much stronger. Because if you think about it, just the solar mass black hole is going to have a mass that's hundreds of thousands of times more than an Earth mass, and it's going to have a distance to the event horizon of 3 kilometers. Earth mass, far, far smaller mass, and is not that much larger a distance from the Earth's center. So there is no black hole. They're in a completely different regime of gravitational force, and there is no black hole at any point. You'd have to be so very far away from a black hole to feel an Earth gravity that you'd be nowhere near the event horizon.
All right, thank you, Chris. The last question that we're going to be able to take for today is from Rana Osama, who's on with us live, who would like to know, how can we test the inflation theory to be correct?
Cosmologists would love to test the inflation theory. It's passed some very simple tests because it predicts that space should be flat, which it is within 1%, but that's not really a very good test of inflation because it was devised to explain the flatness and homogeneity of space. So you can't give it credit for describing something that it was designed to describe. A better test of inflation, and still the best test of it, is that the universe appears to have the power law structure in terms of fluctuations of mass on different scales. And that's a very particular character of fluctuations of density and mass. It's a power law, and not every physical mechanism will give you such a power law, and inflation predicts that. And there's even subtle deviations from the simplest slope of the power law of -1 that also are consistent with inflation. That was devised from the microwave background observations from WMAP and Planck, and that's a pretty good success of inflation theory. Probably the most powerful next level test is going to involve the polarization of the microwave background. And that essentially gets down to the presence of gravitational waves in the mix with the radiation in the extremely high density early universe. And the model makes predictions for what that gravitational wave signature would be and how that might imprint into the polarization of the microwave background. Those are exceptionally difficult measurements. They haven't been successful yet. The BICEP experiment a couple of years ago claimed to have detected polarization, but they were being misled by a foreground signal. So I would anticipate that in a couple of years we'll have this much deeper and more profound test of inflation, where it will either succeed or we'll be left scratching our heads and wondering what's going on with the universe. Thanks very much for all your great questions today, from solar system to cosmology, the usual good range, and we'll be back with you in a couple of weeks. Thanks to Matthew for running the session.